Okay, so as stated in the last video where we looked at just an animation of sampling distributions of a sample mean, I kind of said, all right, there's three big things that we're looking at this at the end of the video. They lead into a theorem. In the last videos, I kind of wrote everything out. Notice it was taking a lot of time to do that, and then if you wanted to, you could just pause and look at these words or hop on Canvas and get the notes. So I just kind of wrote this stuff down and figured I would talk about it, go over it a little bit, and then when I actually go through and do the computations, I'll be writing those, just like I did in the last set of videos for Chapter 11. But basically, when we are looking at that animation video, we should have kind of gotten three ideas. So the first one is that even if we start with some crazy distribution, if we take enough samples, then what would happen with that is as the sample size gets bigger, our sampling distribution of the sample means is less skewed, meaning it became more and more and more normal, looked more like a bell curve. Okay, second big thing that we got to is that the mean should always be approximately the same, regardless if we're looking at the sample mean, the population mean, the sampling distribution of the sampling mean. So we kind of looked at that, meaning that we could use those three things to approximate one another, which is what we are going to do. Okay, the third big idea is when we looked at that sampling distribution of the sample means, we saw that our skew became more normal, meaning our values got closer and closer and closer together. So our data was less spread out when we looked at the sampling distribution of the sample means. So that implied that we had a smaller standard deviation. So these three ideas kind of bring us to one really big, really important theorem in statistics, and that's called the central limit theorem, which I'll abbreviate CLT if I'm ever talking about it on the notes or during the recorded lectures. Okay, so basically the central limit theorem says that when we're randomly sampling from any population with a mean mu and a standard deviation, we've been calling it sigma, if n is large enough, this text considers n greater than or equal to 30, that value kind of wavers between 20 and 40, depending on which text and which statistician you're talking about. But anyways, in general, the bigger the better for the sample sizes. But regardless, if n is large enough, we'll say greater than or equal to 30. The sampling distribution is going to become approximately normal. So if I run through that process we saw the animation for, the sampling distribution will become approximately normal. Right. Thinking in terms of math, we probably all have an idea that if we see the same thing happening over and over and over and over again, it becomes something formulaic or algorithmic, meaning we can use the same thing each time for this. And so what we're going to do is look at this formulaically. So there's a couple things that the central limit theorem tells us in terms of computations, and then we're going to take that and we're going to apply it to doing actual computations. So I'm going to slide this up a little bit so you can see what's down here. Okay. But basically, this idea, that animation that I showed you, the central limit theorem, tells us that computationally, the population mean is approximately equal to, this just means the mean of the sample means, which is approximately equal to the sample mean, which means that we can use all of these things as estimators for one another. Okay, when we do this, what we need to do though is adjust our standard deviation. So if we have the population mean and we've pulled some sample for it, we have to adjust that. So the way that we adjust it is dividing by root n. Thinking about how this relates to the three big things we're talking about, we should know mathematically if we divide a number by something, it becomes smaller, right? So if I say have 4 and I divide it by, 16. So if I take 4 and divide it by root 16, I know that I would get 1. Well, now let's say I want to take 4 and divide it by the square root of 25. That's 4 over 5. That's slightly smaller than 1. So as n gets bigger, as our sampling size or as our repeated process gets larger and larger and larger, our standard deviation becomes smaller and smaller and smaller, and that means that our measurements and our predictions become more and more accurate. So basically this is just illustrating my standard deviation becoming smaller with the larger sample size that I take, or the larger amount of distributions that I pull gets bigger. Okay, so the standard deviation is adjusted and gets smaller as we pull more samples. Okay, so I'm going to use these ideas to do some computations. We'll start simple and then get more complex as we go through this. Okay, so first, I'm going to pull this guy up here, do a couple examples here. Okay, so let's say that we go through and we choose a simple random sample of 4 boys among 4-year-old boys whose cholesterol levels are normally distributed with a mean of 170 and a standard deviation of 30 milligrams per deciliter. Okay, that's just the measurement of cholesterol. Okay, you can calculate the, let's see, oops, the standard deviation, I should say. You calculate the simple random sample, do this multiple times. Oh, I see what we're saying. Okay. Basically, we're looking at the adjusted standard deviation. I think I messed up the wording. I started writing it really fast for that. But if we're looking at this, what's going on is we have a bunch of data, a bunch of population data about 4-year-old boys. Okay, we're pulling 4 samples from this. So we're taking a simple random sample of this, and then we're doing calculations. So what this wording is looking at is if we're doing this, how would we have to adjust the mean for these calculations? Or how would we have to adjust the standard deviation for these calculations? So I know that my mean, just in general, for 4-year-old boys, okay, my mean just in general for 4-year-old boys was 170. So I know that mean is 170. Okay, and here my standard deviation for the population was 30. So population standard deviation, which we've been calling sigma, is 30. Now, if I want to adjust the standard deviations, let's say I want to predict something about a sample mean, I need to adjust the standard deviation. So what I would do is look at the adjusted standard deviation. Okay, that's just going to be sigma over root n. Well, here my sigma is 30, and my n value was 4 because I took a simple random sample of 4 boys. So n is 4 because we took a simple random sample of 4 boys. So we have that divisor there. Okay, here the square root of 4 is of course 2, so 30 divided by 2 is 15. Okay, so of course we'll move along and eventually do calculations with this, and you'll see how the mean comes into play. But for now, we're just looking at how would I adjust the standard deviation in this scenario. Okay, let's try one more of these before we move on to kind of the more complicated examples. Okay, so next example. Okay, it says a recent study was conducted on pigs fed with GMO and non-GMO crops. It was found that on average, pigs fed with GMOs had 2.6 times more stomach, I should say inflation than those without, with a standard deviation of 0.655. Okay, so from this wording, just found that on average, in general, pigs fed with GMO had 2.6 times more stomach infection than those without. Okay, and then let's see, that had a standard deviation of 0.655. Okay, so with this, we choose a simple random sample, SRS, of 16, so my n equals 16 pigs from this group, and average their inflation. If you do this multiple times, what are the mean and the standard deviation? Okay, so the mean we could just use as this. We could use to predict other values, but if we're looking at the standard deviation, we would have to adjust that. So the adjusted standard deviation would be sigma over root n, again. Okay, we have population data and we're pulling a sample of it, so population standard deviation, sample size. Okay, and we would just have 0.655 over the square root of 16. Okay, and of course you could find the value for that, and I would say if you're finding this value, you should be rounding to 4 places on that. So helpful to round to 4 places if you're doing that. Okay, so let's see if we do that. Calculator work there. I'm going to use a lot of decimals to be a bit more accurate. I have 0.16375. Okay, so round to a lot of decimals, so you're kind of holding accuracy as you go through this. But basically, you start with population information, you're drawing a sample, you're going to need to adjust the standard deviation. But of course, now we want to see, okay, well, what are we actually calculating when we're adjusting the standard deviation? So let's take it one step farther and do an actual calculation with this, an actual probability calculation involving our adjusted standard deviation. So let's do even more applications with this, and this time we are going to use our normal distribution. We are going to go back to using our tables and just apply this even more. Right, so first example says, a patient's doctor is concerned that she may have gestational diabetes A patient is classified as having gestational diabetes if her glucose level is above 140 milligrams per deciliter 1 hour after ingesting a sugary drink. Okay, so if you have a kid or know anybody who does, a lot of times this is basically when pregnant moms have too much sugar in their bloodstream. What happens is you drink super sugary drink, and then they basically test to see how much sugar you still have left in your body. Okay, anyway, this level in general, so for the population, varies with a mean of 125 milligrams per deciliter and a standard deviation of 10 milligrams per deciliter. Okay, so if a single glucose measurement is made, what is the probability the patient is diagnosed with gestational diabetes? So we want to think, okay, if one single measurement is made from this person, what is the probability that they're going to have gestational diabetes? Okay, we know this happens if her glucose level is above 140 milligrams per deciliter. So now, what we're going to do is kind of combine all that together with our adjusted standard deviation and kind of the same computational process that we used in chapter 11. I'll explain each step and write it up here. Okay, so going through this, I know that the patient has gestational diabetes if the level is instead of above, so greater than 140 milligrams per deciliter. Okay, so what I want to do is calculate the probability that that's going to happen. We haven't made this measurement yet. We just want to calculate the probability this is happening. So what we're doing is taking the probability that this sample average, okay, so sample average, this time the sample size is only 1 because there's just one patient and we're only gathering one value, is greater than 140. Okay, to do this we need to use some information. So we know that the mean, so we want this, okay, we know that the mean value, just in general for the population, is 125 milligrams per deciliter. Okay, that's the population mean. We know the population standard deviation is 10 milligrams per deciliter. Okay. So now to go through our calculations, we're looking for the probability that X bar, that's sample mean, is above 140. Well, my regular mean is 125. I'm going to center that here. I know if this person has a level of above 140, then they're going to have gestational diabetes. So now I want to calculate this probability. The process will be very similar to what we did before. Okay, so first we drew a picture. Okay, second, before we run through our calculations, I need to do one more step, and that is calculate or find the adjusted standard deviation. Okay, so for this, that's sigma over root n. Okay, so our sigma is 10, and here our n was just 1, so it ends up just being 10. Take note that, of course, if you just have 1, that's not the most accurate, so in general, the bigger the n value, the better that adjustment will be, the more accurate it will be, but it doesn't mean we can't do it with only 1 as our n value. Okay, so from here, I've adjusted my standard deviation. Everything else follows exactly from what we did from chapter 11, at least in terms of just computations. So third, I need to calculate the z-score. Calculate the z-score. Okay, with my adjusted standard deviation. Okay, so here I'm going to have z equals, okay, I'm looking at the value 140, so 140 minus 125, that's my mean, divided by technically 10 over square root of 1, or you could just write 10 if you wanted. Okay, so if we do this calculation, we'll see that we get 1.5. So we get the z-score of 1.5. Now I'm just going to follow exactly what we did in chapter 11. So I need to look up z equals 1.5. Right, so I'm going to use the same normal distribution that I've been using for the notes in general. As soon as I grab it. Okay, so now if I come here, I go down to 1.5, that's technically 1.50. I see that my probability there is 0.4332. Okay, so we get 0.4332 2. Right, so get my colored pens out here again. What this tells us is that this piece right here is 0.4332. Okay, but notice I don't want that piece. What I want is this pencil that's shaded. So what I have to do is a process that we've done before. I need to notice this whole piece right here is 0.5. So to find the probability that sample mean is greater than 140, I would take my blue, so 0.5, and subtract my green, 0.4332, which would give us, let's see, 0.0668. Okay, so if we do this, we would say the probability the person has gestational diabetes is 0.0668. Or you can say there's a 6.68% chance that the person has the gestational diabetes. Okay, so now that we've seen that, notice that the sample size for this was just 1. So I'll do another example where the sample size is slightly larger and we can kind of see what that does. So let's do another example that's somewhat similar to this. So this time, still looking at sort of a medical thing, but same kind of idea. Okay, so hypokalemia is diagnosed, or kalema I should say, when blood potassium levels are low. So below 3.5 MEQs per deciliter. Let's assume that we know a patient whose measured potassium levels vary daily according to a mean of 3.8 and a standard deviation of 0.2. Okay, so here, our person is just the population, but they're getting their blood drawn a lot. So in general, these are the levels that their blood have, but of course we can take samples of this one person's blood. So that's kind of what we're going to do throughout our calculations. Okay, so first part, if only one blood measurement is made, what is the probability the patient will be misdiagnosed as hypokalemic? So basically, we know if the level is below 3.5, then they would be diagnosed as hypokalemic. All right, so we're going to go through this. We only have one blood measurement. That would be our N size here. Okay, so for this part, we know in general that the mean is 3.8. The standard deviation of levels in this blood is 0.2. Okay, our N size here, because we're only taking one measurement, is 1. Okay, and I know that I want to calculate the probability that we could either write X bar, or we could just say that the blood level, so let's say X bar, is less than 3.5, means that this person is has hypokalemia. Okay, so this is the probability we're looking at. Right, so first, I'll draw my picture. So I have my normal curve. My mean here at the center is going to be 3.8. Okay, I know that if this person has a level of less than 3.5, then they have the hypokalemia. So this is what I'm going to be calculating. Okay, so I drew my picture. Now I want to adjust my standard deviation. Okay, so I would have sigma, which is 0.2, over square root of n, which was 1 in this example. So we have 0.2. And from here, I run through similar calculations that I've done. So third, I need the z-score. So we would have z equals 3.5 minus 3.8 divided by, just be 0.2 over root 1. Or you could just write 0.2 if you wish. Right, if you do the calculator work there, you should get negative 1.5. Okay, so here, this is really similar to the first example. Part B will be slightly different. But anyway, calculating that probability now, we need to look this up. Okay, using the same process, we get 0.4332. Okay, so here, even though this is negative, I know my bell curve is symmetrical. So on this table, I can still look up a positive 1.5. The value is the same since the bell curve is perfectly symmetrical. Okay, so that's what I get. Therefore, I know the probability that x bar is less than 3.5 is equal to the 0.5 right here, so 0.5 minus the 0.4332 I get here. Okay, so that gives me the same thing I got last time, which was 0.0668. Okay, so the probability misdiagnosing is 0.0668. So let's continue with this example, but let's see what happens if we make 4 measurements. So if you're thinking about this intuitively, you're just thinking, okay, what do I think is going to happen? Well, if we're taking 4 measurements, remember it becomes more and more accurate, closer and closer to normal. So theoretically, I would think if I'm making more measurements, my standard deviation is going to be even smaller, so the probability of misdiagnosing would be even less. So I think, all right, well, the more samples I take, the more accurate this is going to be, so the likelihood of me misdiagnosing this is going to be even less. But let's go through that process and see that that is actually true. Okay, so this time we're still using the same info. We have the mean at 3.8, population standard deviation, the blood standard deviation is 0.2, but now my n size is 4. Okay, I'm still focusing on the probability that x bar is less than 3.5. Okay, so my picture still looks the same. Okay, but what's different about this one is my adjusted standard deviation. So I drew my picture. Let's adjust the standard deviation. Okay, so we would have sigma is 0.2 over my n would be √4 this time. And now my standard deviation is smaller. So let's see, if you calculate that out, it should be, let's see, 0.2 divided by 2 would give us a, I didn't write it out, that's okay. You can use a decimal or just do it like that, it doesn't really matter. Okay, so that's our adjusted standard deviation. I'll use this to calculate my z-score. So third, we need our z-score. Okay, that's going to be 3.5 minus 3.8 divided by my adjusted standard deviation, so 0.2 over √4. If we calculate that out, we get a -3. Okay, so now, again, I'm going to look this up. Look up. Okay, when we do that, going to my table, I know I can look up the positive value since it's perfectly symmetrical, and I would see that I get 0.4987. So I get 0.4987. Okay, so what that tells me is that this piece right here is 0.4987 based on the table that I'm using. Well, I want this shaded pencil piece right here. So again, I know this whole half, this whole piece is 0.5. Therefore, for my probability that x bar is less than 3.5, I have my blue piece, 0.5, minus my green piece, 0.4987. If you calculate that out, we would get 0.0013. Okay, so this means that the probability of misdiagnosing is 0.0013. Okay, so as we would have guessed, by adjusting that standard deviation, it became smaller, which means that the z-score became larger, moving this guy over here a little bit more to -3. So the z-score became larger. Therefore, our probability became even smaller. So now our probability of misdiagnosing is smaller because taking more and more samples gives us more and more accuracy. So it just means that that population mean is a better predictor for our sample mean when we take more samples, which is illustrated with this example. Okay. Alright, so now go ahead and try a couple more. So this is kind of moving on here. So let's do even more examples using the same idea, and then we're just going to look at some theoretical type questions. Okay, so even more examples. We don't have as much room on here, so I'm going to write kind of small with this. That's okay. Okay, so extra examples. This one says the lengths of individual